Let's take a look at something called kinetic molecular theory. Now, there's some of this that you have to remember from a previous objective, particularly that temperature is the average kinetic energy of the particles of a substance. So that means the average energy due to motion of all these particles, and that depends on the mass. If I change this from neon to argon, argon has more mass, and you'll watch the temperature goes up. And it also depends on the speed. On average, the faster these are moving, the higher the temperature. What we're going to be looking at is an explanation of why solids, liquids, and gases behave the way they do based on a few assumptions about how these particles, these atoms, move. And that is what the kinetic molecular theory is. It's a theory that explains the behavior of solids, liquids, and gases, but primarily gases, based on the idea that the particles of matter, atoms and molecules, are these small hard spheres that are constantly moving. And there are three underlying assumptions, and we're going to use this simulator to take a look at these three assumptions. So the first assumption of kinetic molecular theory is that atoms are small, hard, and don't have practically any volume. So you can think of these as being these little tiny dots that don't take up any space, and they're really, really hard. So that's the first assumption. Notice how simple these are, and it's amazing what they predict when you put them together. So again, they're small, they're hard, like you can't, break them, bend them, etc., and they take up practically no space. Second assumption is that they are always moving, and they're moving very quickly, and they're moving in a random direction. So you can pick any of these particles that you see here. They're moving very quickly and in random directions. And this is the kinetic part. They're moving constantly. And this relates to temperature. The faster they're moving, the higher the temperature. The third assumption of kinetic molecular theory, remember the first is that these are hard, small, and take up no space. The second, that they're always moving in a random direction. And third, and finally, collisions between these are always elastic. That is just really a fancy way of saying that kinetic energy is conserved. The amount of kinetic energy they both have before and after is exactly the same. There's no change in it. Another way of thinking of this is that none of the energy gets put into the internal body of the atom. So you remember, energy is the ability to do work, and it's stored in all kinds of forms. Most of the time what happens with collisions is that the body of one of the objects in the collision will bend. If you think about a basketball bouncing on the ground, the bottom of that kind of squishes in a little bit before it bounces back up. What happens is the amount of internal energy is then increased. The temperature of it increases slightly from where it is bending and then moving back, and the atoms rub together. What we assume about collisions between atoms is that there's no bending, there's no change in temperature internally for the parts of the atom, which I know probably doesn't make much sense right now. These atoms just act almost like perfect, if you've ever played pool, they act like perfect billiard balls. They click off each other without changing shape at all. And that's called an elastic collision. And really with just these three assumptions, as we'll see later on when we talk about solids, liquids, and gases, you can predict a huge amount of information about these phases of matter.